Okay, in this video we are going to prove the characterization of plane graphs. Okay, this particular characterization is known by the name Kuratowski's theorem. Okay, so we will use that theorem, Kuratowski's theorem, to prove that certain graphs are non-planar. Okay, so from the previous video, from my previous video, we know that K5 is non-planar and K33 is also non-planar. Okay, so that says if you have a graph G and if K5 or K33 occur as a subgraph of that graph, then certainly that graph will not be a planar graph. Okay, it will be non-planar. So that says, okay, if G, an arbitrary graph G contains a non-planar subgraph, okay, then we can very easily see that then G is also non-planar. Okay, so similarly we can see that if G contains, so we know that these two graphs are non-planar, K5 and K33. So that says if G contains a non-planar subgraph, in this case if G contains either K5 or K33, then we are sure that that graph is going to be non-planar. So here the reason is because of this thing. For example, suppose that we have a graph which looks something like a K5. Okay, so here we have our K5. Okay, so we have our K5, and suppose that I am going to add, this is K5, right? Okay, one more edge. Okay, so this is our K5, and suppose that we add, say, 3 more vertices and say these edges to this graph. Okay, we can see that this graph is not a K5. So we have a K5 which occurs as a subgraph of this particular graph. Okay, let me call this graph G. Okay, a K5 with some more vertices. Okay, these 3 vertices and these edges. Okay, and here we can very easily see that if this particular graph it has a planar drawing, and okay, if this graph is a planar graph, then definitely it will have a planar drawing. So that says we can take the planar drawing of that graph, okay, of this graph G, assuming that this graph G is planar. Okay, then we can delete these vertices, okay, these 3 vertices and these edges. Okay, so if we delete those vertices and edges from that plane drawing, then we will get a plane drawing for K5. But we know K5 is non-planar. On that says, okay, this particular graph G is also non-planar. Okay, so as I said, if you assume that this particular graph is planar, then there is a plane drawing. You take that plane drawing and delete all these vertices, okay, all these these 3 vertices and these edges. Okay, then the remaining plane graph corresponds to a planar embedding or a plane graph or a plane drawing of K5. But we know that K5 is non-planar, so that is not possible, and that says this graph is also non-planar. Okay, and that says if J contains a non-planar subgraph, then the graph G is non-planar. So if you look at this graph, okay, it has K5 as a subgraph, so it is not non-planar. Similarly, okay, if a graph contains K33 also, the same kind of argument is applicable. Okay, so let's look at another example. Suppose that we have again a K5 looking graph. Okay, it is not K5, so it looks similar to a K5. okay, but it is not KFI. Okay, let's consider this particular graph, and suppose that this graph has a these two vertices and these edges. Okay, here we can see that this graph, it doesn't contain K5 as a subgraph, but it looks almost similar to a K5. Okay, so that says if we delete these two edges and this vertex, and these two edges and this vertex, and if we connect these two vertices by an edge and these two vertices by an edge, then it will become K5. Okay, so it looks something like a K5, but it doesn't have K5 as a subgraph. And here again we can see that, okay, let's call this graph say G dash, and again we can see that, okay, this G dash is also non-planar. Okay, the reason is that suppose that this particular graph G dash is planar, then there is a plane drawing. So what you could do is you could take the plane drawing of this G dash and then replace these two edges and this vertex by a single edge, and these two, delete these two edges in that plane drawing and this vertex, and if we add an extra edge, okay, then we get a K5. Okay, and that K5 we get a K5, and that corresponds to a plane drawing of a K5. Okay, and that says G dash is non-planar. Okay, so let me repeat the argument here. If you assume that G dash is planar, then there is a plane drawing. So you take that plane drawing and delete these four edges and these two vertices, and insert an edge between this vertex and this vertex, and an edge between this vertex and this vertex. Okay, and that plane drawing will correspond to a plane drawing of K5, but we know K5 is non-planar. Okay, and that says this G dash is also non-planar. Okay, so if have a plane drawing for this thing, then we could convert that plane drawing to a plane drawing or a planar embedding of K5. Okay, and since K5 is non-planar, G dash is also non-planar. Okay, and such an operation, okay, deleting such a thing is what is called a subdivision. Okay, so here this particular graph, it is a subdivision of it's a subdivision obtained from K5. So here the subdivision means, okay, you start with a K5. Okay, so if you start with a K5 which looks something like this, okay, we can see that, okay, from this particular phi, so we have this K5. So if we take this graph and if you do a subdivision operation, and subdivision operation something like this, okay, you take a particular edge, delete that edge, then insert a new vertex and add these two edges. Similarly, delete this vertex, this edge, okay, insert a new vertex and these two edges. So if you do that operation, then we get this graph. Okay, that is called, and that says this particular graph G dash is a subdivision obtained from K5. Okay, and that says this graph, it has a subdivision of K5. Okay, so let me make that definition clear. So that is called an elementary subdivision. So if a graph, we can see very easily see that if a graph is planar, so will be any graph obtained by removing an edge UV and adding a new vertex W together with edge UW and WV. Okay, for example, okay, let's consider a very simple graph kind of thing. Okay, so let's look at this K4. So we know K4 is regular, is planar. It is also regular. Okay, it's also planar. And okay, we have this plane drawing. So if we take this plane drawing, and we can see that any graph obtained by removing an edge. Okay, suppose that we remove this edge. Okay, so if we remove that edge, we get this graph. Okay, so we get this graph Okay, so remove that edge, then add a new vertex W. Okay, so this is our vertex W. Suppose that this is U and this is P. Okay, so we did delete this vertex, this edge first. Okay, then add a new vertex W together with these edges. U is here, V is here, UW and VW. Okay, we can very easily see that this graph is also a planar graph. Okay, so that's what this bullet says. If a graph is planar, so will be any graph obtained by removing an edge UV and adding a new vertex W together with edges UW and WB. Okay, and such an operation is called an elementary subdivision. Okay, so for example, if you look at this particular graph G dash, we can see that okay, this G dash can be obtained from K phi by two elementary subdivision operation. Okay, so first the elementary subdivision operation will be like you take a K phi, okay, remove this edge and insert this new vertex and these two edges. Okay, that is one elementary subdivision. And do one more elementary subdivision operation. Okay, take this edge, delete that one, insert this new vertex and these two edges. Okay, so this graph G dash can be obtained from K phi by two elementary subdivision operations. Okay, so such an operation is called an elementary subdivision operation. So here from this example we can see that okay, after performing the elementary subdivision operation, if the original graph is planar, then the new graph which is obtained by an elementary subdivision is also going to be planar. Similarly, if you take this particular graph and if you do one more elementary subdivision, okay, for example say something like this, okay, you can take any edge of this one. So here we have this graph, okay, which is a planar graph. Okay, so you can take any edge of this graph. Okay, for example, suppose that we take this edge and we delete that one and insert one more vertex and these two edge. Okay, again we can see that that graph is also a planar graph. Okay, so this graph is obtained from this graph by performing this elementary operation. Okay, again we can see that this graph is obtained from this graph by performing two elementary operation. Okay, first we deleted this edge, inserted this vertex W and these two edges. Okay, so we get this graph, and from this graph we obtain this by deleting this edge and adding this vertex and these two edges. Okay, okay, so that is called an elementary subdivision. So okay, this is another example. Okay, if you consider these three graphs, we can see that suppose that this is a G1, this is G2 and this is G3. Okay, so G1 itself is an elementary subdivision, so we can get G1 without performing any elementary subdivision operation. Okay, so 0 or more elementary subdivision operation. Okay, similarly we can see that this G2, it can be obtained from G1 by three elementary subdivision operations. Okay, so first delete this edge, okay, and insert this vertex F and these two edges. Okay, and then take this particular graph G2 and okay, delete this edge and insert say this vertex and these two edges. Okay, then take that graph and insert okay, take that graph and consider this edge GB, delete that, insert this new vertex and these two edges. Okay, this edge and this edge. Okay, so let's say G2 can be obtained from G1 by those three elementary operations. Okay, and similarly we can also see that this G3 can also be obtained from G1 by 1, 2, 3, 4 elementary operation. Okay, maybe first in the first elementary operation we deleted this edge and inserted this vertex and okay, these two edges. Okay, and in the next elementary operation we might have considered this edge GB, delete that edge, insert this vertex J and these two edges. Okay, and the next elementary operation we deleted this edge and inserted say K and these two edges. Okay, and the next operation we deleted this edge KE, inserted this vertex and these two edges. Okay, so that says Okay, G2, it can be obtained by performing 3 elementary operations on G1, and G3 it can be obtained from G1 by 4 elementary operations. Okay, so this is how we define an elementary subdivision. So let x equal to ub be an edge of a graph. The edge x is said to be subdivided when a new vertex w is added to G, and the edge x is replaced by edges u, w and v, w. Okay, so as I said, okay, so it will be something like this. Suppose that we have this graph, and suppose that this is our edge x, which is equal to uv. Okay, then x is said to be subdivided when a new vertex w is added to G. Okay, so what we do is, okay, we will take this graph. Okay, we delete this edge. Okay, this edge x is replaced by new two edges uw and wv. Okay, after inserting a new vertex w. Okay, so this is our u, this is v. Now we have these two edges uw and vw. Okay, this process is called an elementary subdivision of the edge x. Okay. So using the definition of this subdivision, we can define homeomorphic graphs. So definition says two graphs are said to be homeomorphic if both can be obtained from the same graph by a sequence of subdivision of edges. Okay, so let's look at this particular graph, and let this graph be G, H and say K. Okay, so here we can see that, okay, this K, H can be obtained from G by 3 elementary subdivisions. Okay, so we explain how this can be obtained, right? First, what we do is we take this edge, remove that one and insert this new edge and these two edges. Similarly, in the next elementary operation, okay, take this edge CB, delete that, okay, insert this vertex and these two edges CG and GB. And the next elementary operation, we take this edge GB, okay, delete that edge, insert this vertex and these two edges. Okay, so H is obtained by 3 elementary operations, performing 3 elementary operations on G. Okay, similarly, we can also see that this K can be obtained from G by performing 4 elementary operations. Okay, so that says, okay, this H is, okay, H and K are homeomorphic. Okay, homeomorphic. Okay, we can see that we can obtain this H and K from the same graph by performing, okay, some number of elementary operations. Okay, so two graphs are said to be homeomorphic if both can be obtained from the same graph. So here H and K, they are obtained from the same graph G by a sequence of subdivisions of the edges. Okay, so that says H and K are homeomorphic. Okay, so they are homeomorphic. Okay, using this we can define, okay, this we can state Kuratowski's theorem. So we want to prove this theorem, so it takes many videos to prove this thing. Okay, so we skip the proof of Kuratowski's theorem. So that says a graph is planar, okay, if and only if it has no subgraph homeomorphic to K5 or K3. So that says, okay, if a particular graph has a subgraph homeomorphic to K5 or K33, then the graph is non-planar. Okay, so let's look at this graph. So here we have our K5. So it's a graph, a complete graph on 5 vertices, and here we have these two graphs G and H. Okay, here we can see that this H is a subgraph. Okay, it is a subgraph of G. Okay, we obtained this H by, okay, deleting, okay, these two edges I and this vertex, and okay, deleting these two edges and this vertex, okay, and deleting okay, these two edges and this vertex. So that says H is a subgraph of G, okay. So H is a subgraph of G, and if you look at this particular graph H, this subgraph H, we can see that we can obtain this subgraph by performing 1, 2, 3 elementary transformation on this KFI. Okay, so if you take this edge, okay, GC, delete that, then insert this vertex D and these two edges, okay, DC and DG, okay, and again perform an elementary operation on this graph. Okay, take this edge GD, remove that, insert a new vertex, okay, insert a new vertex, okay, let's call that vertex E, and insert edges GE, ED, okay, and I think one more elementary operation, take this edge GE, delete that edge, insert this vertex F and these two edges GF, FE, okay. So if you perform, okay, those three elementary operations on KFI, we get H, okay, and that says this particular graph G, it has K5, it has a subgraph that is homeomorphic to KFI, okay. So this G has a subgraph H, okay, that is homeomorphic to K5, okay. So K5 by itself is homeomorphic to K5, and similarly we can see that this graph H can be obtained by these three elementary operations on K5. So that says H and K5 are homeomorphic, and here we can see that this graph G, it has this subgraph H, and this H is homeomorphic to K5, a non-planar graph, okay, and then applying, okay, so applying by Kuratowski's theorem, okay. So by Kuratowski's theorem, okay, this graph G is non-planar. Okay, so this is how we use Kuratowski's theorem to show that a graph is non-planar. So if you are able to find a subgraph, okay, that is homeomorphic to either K5 or K33, okay, then that is enough to say that the graph is non-planar, okay. So we will see one more example in the next video. So in the next video we will prove that Peterson graph is also non-planar, okay. Okay, so here the definition of homeomorphic graph and elementary subdivision is very clear, right? Two graphs are said to be homeomorphic if both can be obtained from the same graph by a sequence of subdivision. Here we can see that these two graphs H and K are homomorphic because they can be obtained from G, okay, same graph G, and similarly we can also see that G and H are homeomorphic. So by definition G is homeomorphic to itself without any elementary transformation. So G and H are also homomorphic, and similarly G and K are also homeomorphic, okay. And elementary subdivision is nothing but taking an edge, deleting that edge and inserting a new vertex W and replacing that edge X UV by two edges UW and BW.